So this is the introduction for our forthcoming the CubeSat satellite. Then well, it's not necessary to explain in the motivation of this study. Of course, everyone knows we would like to mitigate in the earthquake detection. Of course, if we can predict earthquake into observed from the observing in the precursors, it is quite useful. Then, but so far it's very difficult to predict earthquake in the using in the detection of the precursors. But so we try to this kind of the precursor studies for the earthquake mitigations. Then, so Frantic already explained in the DEMETER result. So I would like to summarize the DEMETER result. This is quite significant. So they publish in the several papers in the international journal. The DEMETER observed electric field intensity depression within 4 hours before earthquake. The pitch magnitude is more than 4.8. Then in the interpretation, so there is a waveguide mode modification over in the earthquake preparation zone. It means electron density increase around in the D region altitude only during nighttime. Of course, this kind of the precursor occurred also during the daytime, but so no way to observe this kind of electron density increase during the daytime. Only we can observe this kind of the signal in the nighttime. From our independent statistical analysis, this kind of depression occurred in the 20 or 30% of the total events. It's not so whole event, but so almost in the 20 or the 30% events, we can observe this kind of depression of the electric field intensity in the VF band. This is the kind of the summary. Then the scale of this kind of the electron density increase over the epicenters almost within 500 diameters in the radius, 500 kilometer radius. Then motivated by the DEMETER result, so the several satellite launch after the DEMETERs. The most famous one is the Chinese satellite, so-called CubeSat. This satellite is launched in the 1918, and these are first satellites. They planned it in the total 5 satellites, so they are listed completely for the space science. Then second satellite will be launched soon, quite soon. Then the first practical satellite for the dedicated to this kind of earthquake study is DEMETERs. This is a microsatellite. The weight is not so large. It's a so-called microsatellite in the 130s, in the almost a small satellite. And they used in the Russian Dnieper rocket for the launch. And the cost is almost in the same of the rocket cost. And they use X-band for the communication. They put one ground station in France. And so in China, so they integrated in the satellite. So they copied the DEMETER system, and also they integrate in the additional payload embedded in this satellite. And then they use their own long March rocket. Then they have the full receiving station in the ground. Maybe they used a lot of money for this kind of studies. And also there is a very small satellite developed by Kazakhstan, and this is a very small 3U CubeSat, and a very small one, and they used in the UHF band and in the amateur radio band, and so they did not put the electric field measurement. The DEMETER uses the electric field and the measurement. Also, the CubeSat also has the electric field measurement payload. But so in the Kazakhstan satellite, they don't have the electric field measurement. They use a magnetic measurement only. And so for us, So for our satellite, it's not so large. In the 6U site, it's very small, still small. But so this is only dedicated to the study of the DEMETER result. And also, our idea is integrated in the DEMETER result. Then our satellite is already selected by the JAXA. So we launch maybe in the end of the 2024 or the early 2025, already decided. Then we use S-band for the communications. And also, we use ground station. It means we can use the many radio ground stations globally. This is our advantage. And the cost is very cheap. We cannot compare the other satellites. It's quite cheap. This is a 6U satellite. And so we use the piggyback system in the JAXA's rocket. Then so that there is no charge for the launch. The basic idea is quite simple. So our satellite is a quite simple small satellite here. Then so maybe altitude around 550 kilometers at this moment. Then so usually so a lot of lightning occurs on the ground. This kind of lightning generate in the radio wave. So this kind of radio wave that partially penetrates into the ionosphere. Then usually we observe the radio wave at the satellite altitude. But once electron density increase as a precursor or the other reasons, and so this kind of the radio wave from the lightning and absorbed at this kind of electron density enhanced regions. So it means so there's no something happens at the D region, so we can directly observe the radio wave from the lightning at the satellite altitude. But so this kind of the precursory electron density increase occurs. So it means that we observe the decrease of the electron, we observe the electron field in the small intensity. Then, so for example, so we have the barriers in the ground stations, so-called the cloud ground stations. So we can emit, we can send a lot of the data. And so the point of this study in we observe the lightning waveform, lightning signal waveform. It means that so this kind of the signal includes the information of the electron density information at the D region altitude. So in the and also our target is the quite clear. We just waveform observations in the earthquake event and also the before earthquake, after the earthquake as a control orbit. Then this is the list of the data acquisitions. So we observed and electron field in the spectrum. So this is a copy of the DEMETER. But so the frequency of the sampling in the twice than the DEMETER sampling. And so this is survey, so-called survey mode, continuous. And also we continuously observe the high sampling. So because we can observe, want to observe in the waveform of the lightning signal. But so it is very difficult to send the whole data. In the DEMETER, they only observe the limited regions, the limited region of where the seismic activities is very high. Only the limited region. But so in our case, it's not different. Our case is once earthquake occurs, so we know this kind of information immediately from the ground observations. We send the information in the satellite, uplink command. Then we ask the satellites to send the data in the earthquake orbit and the control orbit. Then so we pick up the data from the database in the drive recording system. And so we send the whole data of this kind of the relatively large earthquake as a DEMETER, as a burst mode. This is completely different from the DEMETER system. And also additionally, so we also observe the GL satellite, TC. This is not a radio carrier station, but so we observe the TC. This is good for the Professor Liu's result. So we observe this kind of the TC. And also, this is also follows the Professor Liu's result. We also observed in the plasma parameters using the Langmuir probe. And so that we have the housekeeping data. The total amount of the data is almost 100 megabytes per day. It's not so large, so we can send the data in the S1. Then, so this is the comparison between the expected detection of the events. That is a compare between the DEMETER and the PRELUDE. As I mentioned before, DEMETER only observed in the burst mode in the very limited region. It means that only the high seismicity regions. Then, but so in our satellite, and we send the command, and once earthquake occurs in near the satellite, then so we pick up the effectively data. Then so we observe a lot of the burst data. This is almost doubled of the DEMETER satellite. For example, if we operate in the 1 year, in the more than 100 earthquake events, it is good for the statistical analysis. So in our operations, we planned it in the 2 years operations, but so at least 1 year, we can get 100 events. This is good for the statistical analysis. Then this is our team. I introduce our team. We developed the satellite in mainly the two universities in our University Shizuoka, mainly for the mission design and data analysis. And so the satellite is designed and developed by the Nihon universities. And so we got the support from some of the companies in the well research. They are good for the boom development. And so we asked in the DEMETER, one of the DEMETER team in the Latomos, so we asked them to prepare the electron emitters because our satellite is quite small. So if we observe in the plasma parameters, our satellite, the potential change during the observation of the plasma, then to keep in the stable the value of the satellite potential, we put the electron emitters. Then so we asked in the Latomos in the prepare this kind of the instrument. And also UNISEC in support in our group. And so we asked one company, InfoStella, they provide in the service of the cloud ground stations. We asked them in their ground stations. This is an overview of our satellites. We have the two booms. One boom is 1.5 the meters. In the tip of the booms, we put the hybrid center for the electric field in the plasma. So the plasma measurement, this kind of sensor is applied to the Langmuir probe. And also, in other mode, we can observe the electric potential difference between the two probes. Then, so we can calculate in the electric field using the two probes. Then, so characteristics of study in this CubeSat is only dedicated to the equipration, particularly for the follow the DEMETER result, and also upgrade in the DEMETER result. And so we only use a mature technologies. For example, the sensor is copy of the DEMETER, and so squeeze the DEMETER. And so this is the open design. So we can display this design for the other university. And so this is we use also the dense network monitoring on the ground station. And also our system has the possibility of the dense monitoring network from the constellation because the satellite is very small and very, very cheap. This is a configuration in the satellite spacecraft. So we have the emitters, as I mentioned before. So we have this kind of the boom system. The only 3U space used for the boom. And this is a satellite system bus and also we put the VF receiver inside of this kind of boom, and the boom part. And this is a
Professor
feature.
Kamogawa, 3 minutes, please.
Okay. I'll also finish soon. This is the future plan. You know that we have the 100 aspect during the 12 years in the magnitude more than 7. So the magnitude 1.7 is quite large. So once this kind of large earthquake with magnitude more than 7, the damage is quite large, too large. Then, so if we operate this kind of the satellite continuously using the constellation, so we can meet, we can get the events of the more than 100 earthquake if we satellite covered in the observation. So it means that this is the statistical point of view. The 100 earthquake is good for the science. So we hope this kind of the observation should be 12 years observation. So that is our figures. This is the animation of our satellite view. So we have the precursors. Maybe we expected to observe the precursor over the epicenter. So sometimes we have the many lightning activities, and usually the 50 lightning per second. So we can use the lightning signal and as a kind of radars to observe this kind of precursors. Okay, that's all. Thank you for your attention.